In this video, we will learn how to characterize coordination complexes. And we'll look at these in terms of coordination number, the character of the ligands, the geometry, and the hybridization. We can identify a coordination complex within a chemical formula because it will always be enclosed in brackets. If it's a standalone complex and the complex is an ion, then there will be the charge on the outside of the brackets. If the coordination complex is part of a compound, then there will also be a counter ion shown outside the brackets as either the cation or the anion. The coordination number of the complex will help us to determine the geometry of the complex and its corresponding hybridization. So what is a coordination number? The coordination number will be the total number of bonds attached to the metal ion. And to figure this out, we need to know something about the character of the ligand. So there are different types of ligands that contribute different numbers of bonds. In this class, we will limit ourselves to monodentate, bidentate, and tridentate ligands. Most of the ligands that we will see are monodentate. I've listed here the ones that are not, so that way you can be sure to remember them, and then you'll know that all of the other ligands, except for these three, are monodentate. So the only tridentate ligand that we will encounter is diethylene triamine, which has the abbreviation diene, D-I-E-N. This ligand contributes 3 bonds to the metal ion for each ligand. The 2 bidentate ligands that we have in this class are oxalate and ethylene diamine. And as I mentioned, all of the other ligands that we will encounter are monodentate. It's important to recognize this character of the ligands because a common mistake when determining the coordination number is to count the number of ligands, but we have to make sure we are counting the number of bonds coming from the ligands, and then we add them all up. The coordination number is also connected to the geometry and corresponding hybridization. All complexes that have a coordination number of 2 will be linear, and the hybridization for a linear complex is sp. All octahedral complexes have a coordination number of 6, and that hybridization is D2sp3. And those complexes that have a coordination number of 4 have 2 options for the geometry. They may be either tetrahedral with an sp3 hybridization or square planar with a dsp2 hybridization. How do you know the difference, whether the complex is tetrahedral or square planar? It mostly goes beyond the scope of this class. One thing that I do want you to know is that if the orbital diagram shows that the metal ion is a D10, in other words, there are 10 electrons in the D subshell, those complexes are typically tetrahedral, whereas those metal ions that have a D8 configuration are often square planar. So this is an example of what a coordination complex looks like. As mentioned, it is enclosed within brackets, and if it happens to be an ion, that charge is on the outside. So the first thing we're going to do is we're going to take a look at the ligands and determine if they are monodentate, bidentate, or tridentate. Our metal ion is the silver, so that is not a ligand. And the only ligand that we have in this particular example is ammonia, which is called an amine ligand. Ammonia, or amine, when it's a ligand, is monodentate. So each ammonia molecule contributes 1 bond to the metal ion. So in this example, we have 2 monodentate ligands, where each one gives us 1 bond. And so our total number of bonds is 2, and our coordination number is a 2. Our next example looks a little bit more complicated, but we're going to apply the same strategy. Here's our metal ion. So we're not going to do anything with that, for this particular example. Our first ligand is water. Water is monodentate. And our second ligand is sulfite. Sulfite is also monodentate. To figure out the coordination number, we need to add all of the bonds together coming from all of the ligands. So we have 2 waters, where each water contributes 1 bond, and we have 2 sulfites, where each sulfite contributes 1 bond. And when we add them up, we get a coordination number of 4. And we have one more example, just identifying our metal ion as a metal ion. Looking at the ligands, the first ligand we have is a chloride ligand. Chloride is monodentate. The next ligand we have is ethylene diamine. Ethylene diamine is bidentate. And our final ligand is water. Water is monodentate. So to figure out the coordination number, we have 1 chloride, which is monodentate. We have 2 ethylene diamines, where each ethylene diamine contributes 2 bonds. And we have 1 water, which is monodentate. So when we add all of these up, we end up with a coordination number of 6. So now we're going to look back at those same 3 examples, and we're going to predict the geometry and hybridization for each complex. So for our first example, we determined that the coordination number was a 2. All complexes that have a coordination number of 2 are linear, and the corresponding hybridization for a linear complex is SP. Our next example had a coordination number of 4. Remember, we have 2 options when the coordination number is 4. We might have tetrahedral or square planar. Now, sometimes a question will ask, what are all the possibilities? And in that case, we would say, these are the possibilities, tetrahedral or square planar. In this example, we can actually take that one step further. So if we take a look at the noble gas orbital diagram for zinc, we have argon, 4s, and 3d. If we fill in the electrons for neutral zinc, we would have 4s2 and 3d10. And the other part of this is there are some p orbitals that are empty. So this is what the orbital diagram for neutral zinc looks like. If we then look at what does zinc ion look like, our zinc ion has a charge of a +2. The rule is that when an ion is formed in the d block, we remove the s electrons first, and then any d electrons that we might have to remove. In this case, we are only removing 2, and so it is just those s electrons. At this point, we notice that the d subshell is completely filled. So there is no space for any ligands to attach there. So this is considered a D10 complex because the d subshell has 10 electrons in it. It's completely full. The only available orbitals then for hybridization are the s and the 3 p's. So our hybridization is sp3, and that corresponds to a tetrahedral complex. Our final example had a coordination number of 6. Whenever the coordination number is 6, the geometry is octahedral. And an octahedral geometry corresponds to a hybridization of D2sp3.